Hello folks, and happy Friday. This video covers 6.7, which is about graphing other trig functions. So we've mainly focused on how to do sine and cosine graphs so far this week, but of course we know that there are many other types of trig functions. So this video will cover them. The first thing I need you to remember, if we recall, that sine and cosecant are reciprocals. Sine and cosecant are reciprocals. Okay, so if you remember that, in other words, that means 1 over the sine of theta is how we define the cosecant of theta. So if we know how to graph the sine function, then we can use that and what we know about the property of reciprocals to graph the cosecant function. So let's go ahead and label our axis. We will count by pi over 2 on the x-axis. So I'm just going to skip, this one is pi over 2, and that one's pi 3, pi over 2 and stuff, but you can just skip over and just worry about labeling the whole pi's. And then, of course, on our y-axis, we have 1 and -1 there. Okay, so here are our values for the sine function. Remember, we only care about the 4 corners, right? So if I do my x, y, my first coordinate point is, no, let me not do that yet. Okay, sorry, hold on. Let me go back for a second. Let's actually just go ahead and graph. For sine value, we know the parent function starts at 0. Then we know the next value at pi over 2. The y value at that point on the unit circles up here at 1. And then it just kind of makes a pattern that hopefully you're getting used to by now. And we could also go on the left side as well and do that. Okay, so I graphed that in gray. What I want you to do is, if you have another colored pencil, we're going to graph the cosecant function with this sine function. It's going to be easier for you to understand kind of where it comes from. So what I want to do over here with what I was going to do with my table is I just want to list off some of these coordinates. So like the first coordinate at the origin, 0, 0. The next coordinate has an x value of pi over 2 and a y value at 1. That's this one here. The next coordinate is at pi 0. The next coordinate is at 3 pi over 2, 0. Nope, lies. 3 pi over 2, -1. Pi over 2, -1. And then the next one is at 2 pi 0. So we'll just worry about doing 1 period. Now, reciprocal means 1 over the value, right? So we still have the same x values. That doesn't change because we're still graphing on the same coordinate plane. So I still am going to have the same x values of 0, pi over 2, pi, 3 pi over 2, and 2 pi. The reciprocal is going to be the y value because that's what sine is anyway, right? Sine is concerned about the y coordinates. So if I take the reciprocal of these, it's going to be 1 over that value. So I'm going to look at these y values here and take their reciprocals. Well, 1 over 0 is undefined. So that y value is undefined. Then my next value is 1, and 1 over 1 is just 1. The next value, again, I have 1 over 0, which is undefined. The next one I have 1 over -1, which is -1. And then again I have 1 over 0, which is undefined. So you're going to notice at all of my whole pi values, 0, pi, 2 pi, and it would continue to repeat itself, etc., I have undefined values, which means for the cosecant function, and I'm going to graph my cosecant in a different color. For the cosecant function, we're going to have asymptotes at those coordinates or at those x values. So we said they're going to happen anywhere that they were undefined. This x value of 0, pi, and 2 pi, I'm going to have vertical asymptotes there. So this is the first part to the cosecant graph. And it's going to happen at every whole pi, so I can make my negative pi a dotted asymptote as well. Okay, so now if we did a little bit more exploration as to the points in between, right, like our pi over 4 values and square root of 2 over 2, all that kind of good stuff, we'd get a little bit more accurate curve. But for now, just trust me, if you will. And I'm going to draw my cosecant in blue. What's going to happen is, notice at pi over 2, my value is 1, which is already here, but there's an asymptote. So what happens is it takes the reciprocal of my grade function and it like flips it over like this. Okay, my next coordinate at 3 pi over 2 is -1, which is there, but the cosecant value flips over everything else. And if we continued the process, we'd see that this value would be a +1, and it would look like this. And down here, this value at -pi over 2 would be -1, and it would look kind of like this. So again, I want to be clear that in this graph here, the cosecant of theta is the blue graph, the blue curves. The red are the asymptotes that go along with the blue graph, and the gray is just the regular sine curve. Gray is just a regular sine curve. So the sine of theta is in gray. So if we were to see the cosecant graph in isolation, we would see, I'll show you here, cosecant of theta. If we wanted to see that just by itself, let's see, -pi. So without seeing the sine theta with it, the cosecant would be, remember, you would still draw your asymptotes on all of the whole pi's. So -pi, also at 0, there's an asymptote, at pi, and at 2 pi, and at 3 pi, and at 4 pi, and 5 pi, and all the way up until forever. So they'd have asymptotes. And then it would have these coordinate points. This one here would be at -1. This one here would be at +1. Then this one would be at negative, then positive. And you see the pattern there. And these curves flip outward. So this is what just the cosecant graph would look like, the asymptotes with the curves flipping up and downward forever. So I want to talk about some qualities of this graph, just like we did when we first learned how to do sine and cosine. The first thing I want to talk about is the period. So remember, a period is how long it takes for it to complete one cycle and look the exact same all over again. So a period, again, it doesn't matter where you start it, but it appears that if I look at this figure, it would repeat itself exactly again there. Okay, so that distance from -pi to pi is 2 pi. So the period is 2 pi, just like the other trig functions that we're used to. The next thing I want to discuss is the domain. Domain deals with all of our x values. So clearly we're missing some x values, right? Every time we have one of those red vertical asymptotes, those x values are not allowed. So all of those x values are on pi's, right? So we can say that our domain is the set of all real numbers except pi n, when n is an element of, remember this, when I use z like this is standing for the integers. So that means, this could be 1 pi, 2 pi, 3 pi, -7 pi, 0 pi, etc. Our range deals with what values does this graph, what y values does this graph cover? Well, it almost covers all of them except this blank space in between -1 and 1. So, and you can write that a couple different ways, but I'll just say that our range in regular inequality notation is y's that are greater than or equal to positive 1. That takes care of these curves up top. And then these curves at the bottom, they're almost like a bunch of little mini parabolas. Those are going to be when y's are less than or equal to -1. So those are your range values. The next thing I want to talk about is intercepts, which in this case there is no x or y intercept. Say no x or y intercepts. And then the very last thing we're going to talk about on each one are where, if any, are there asymptotes. Well, your asymptotes are going to coincide with your domain restrictions, right? Because those are the x values that you cannot have. That's why an asymptote exists. That's why it is there. So our asymptote is going to be the same as our exception over here. It's going to be when x is equal to pi n, when n is an element of the integers. Okay, so that's the deal with cosecant. Now, you can totally plug that into your calculator and look at the curve there as well, just like we've been doing, right? Put in whatever kind of window you want. Your table set, you know, count by pi over 2, because that's what these are, counted by pi over 2s. And then you can plug in cosecant, which is 1 over the sine. So since you can't plug in cosecant in your calculator, you would plug in and y equals 1 over the sine of, and we don't enter theta, we put sine of x. So this is what you would plug into your calculator if you wanted to see those curves. Okay, it is not the same as inverse. Not the inverse. We're going to chat a little bit about inverses on Monday. Okay, reciprocals are not inverses. So you're not going to use the second button in input sine inverse instead. You want to input cosecant, which is 1 over the sine of x. Okay, so there's cosecant. The next graph we want to discuss is the reciprocal of cosine. Reciprocal of cosine. So recall that cosine and secant are reciprocals. Cosine and secant are reciprocals. So in other words, 1 over the cosine of theta is equal to the secant of theta. So again, if you wanted to plug that into your calculator, if you wanted to graph secant, you would plug in 1 over the cosine of x. And we could make a table. We could graph the the cosine function, make our table, and then take the reciprocals of those values. But we're just going to rely on the graph here again. So again, I'm going to draw sine and, I'm sorry, I keep saying sine. We're going to graph cosine and secant on the same graph. Let me try this again. Sorry, technical difficulties. Please move. There we go. Okay, so we're going to graph our cosine function first. Again, hopefully you're getting pretty quick at these. Your cosine function, again, our y values will be from -1 to +1. And again, we'll count by pi over 2. So I'm going to skip that one. I'm just going to worry about pi's. On the left side, -pi. Okay, cosine, as long as I'm not shifting it at all, the parent function starts up here at +1. We're going to use 2 different colors. I'm going to use gray. Okay, so it starts up here at +1, and then it goes down to 0, down to pi, back up to 0, back up to +1, and then you can continue filling out the pattern if you'd like. So my gray function here is cosine. So cosine of theta is in gray. If I graph the secant, if I take the reciprocal, so again, we're going to save time. Instead of having to write out our charts, just know that it is very, very similar to the sine cosecant relationship. Our x-intercepts here, since they have y values of 0, when I take the reciprocals, when we divide by 0, we will get an undefined value again, meaning we're now going to have asymptotes at these zeros. So you can graph your asymptotes that intersect these x-intercepts from the cosine graph. So those intersect their x-intercepts, and it will look extremely similar to the cosecant graph. So the secant of theta, I'm going to graph in blue. And what happens is they share these points, these max and min points, except they flip out to the other side. So it'll share this min, but it'll flip downward like this. And it'll share this one, but the curve will go the other way. So again, the blue function alone is the secant. I just wanted to compare. Sometimes it's easy to see it compared with its reciprocal graph to know how to draw it and where the asymptotes should be. So again, let's go ahead and talk about those properties. The period, if you'll notice, if you compared these two graphs side by side, literally they are the same thing except just shifted over, right? It's shifted over a value of pi over 2. So again, if you were to break up and ask yourself how long did it take to go through one cycle, it would still be 2 pi. Okay, our domain is similar to the issue that we had for cosecant, is that it hits all real numbers except, and this one will be a little bit different because these are asymptotes, or sorry, well, yeah, they are the reason for that, the asymptotes. The x values that it cannot equal are all the half pi's, right? Pi over 2, 3 pi over 4, etc. So the way that we can say that is that the domain is all real numbers except pi over 2 in, when n is an element of the odd integers, right? Because if it's even, then the even cancels with the 2, and then you're like, so let's suppose n were 2, then pi over 2 times 2 will be just pi, but there is no asymptote there, so that's why it needs to be an odd integer. Our range is what y values does our graph cover? And again, it's almost all of them except between -1 and +1. So we'll just use regular inequality notation. Our range is for y's that are greater than or equal to 1 and y's that are less than or equal to -1. For x-intercepts, there are none, right? The blue graph does not cross the x-axis ever. The y-intercept, even though cosecant do not have one, secant does have one. It intersects the y-axis up here at 1. So the y-intercept is when y is equal to 1. And then lastly, our asymptotes. Remember we said they coincide with the domain restrictions. Those two things coincide. Therefore, our asymptotes are just going to be the vertical lines. X is pi over 2n when n is an element of the odd integers. Okay, and just to save time, I'm not going to graph secant on its own graph. I'll just leave it there with cosine. Okay, so that's how to graph a cosecant and secant based on our knowledge of sine and cosine. And of course, the last trig function that we have not discussed yet is tangent. We haven't even graphed regular tangent, much less the reciprocal of tangent. So if we have y is equal to the tangent of theta, what I need you to remember is that we discussed when we very first started talking about this trig stuff, was that tangent is equal to slope. Okay, so if I take my 4 corners of the unit circle is what I like to call them, and let's take those coordinates. at the four corners. So my x value at at 0 degrees or at 0 radians, x value is 1, y value is 0. So if you are kind of lost as where I'm getting this from, we got our unit circle, and I want these four coordinate points. So this is 1, 0, 0, 1, negative 1, 0, 0, negative 1. So if I start here in standard position, that coordinate's 1, 0. If I rotate counterclockwise, my next coordinate is 0, 1, then negative 1, 0, then 0, negative 1. Okay, if tangent is slope, and we know that slope is rise over run or delta y over delta x, then we're just going to divide these coordinate points to figure out what the slope should be at each of those points. So for our first one here, y over x would be 0 over 1, which is 0. Then my next pair will be 1 divided by 0, and anything divided by 0 is undefined. My next one, 0 divided by negative 1 is 0. And then lastly, negative 1 divided by 0 is again undefined. So we have this idea of asymptotes again in our tangent graph. Okay, so if we were to graph, and I'm going to make this one a little bit bigger than my others. Okay, so if I've got x-axis, y-axis, again, we're going to count by pi over 2. So here's pi, 3 pi over 2, 2 pi. Okay, so if I have this, and again, we have 1 and negative 1. And I wanted to graph tangent using what we know about these values now. Okay, at our first coordinate of 0, our x coordinate of 0, the slope at that point is 0, so that's an actual coordinate. Then what happens at our next coordinate at pi over 2, we're at undefined, which means we're going to have an asymptote there. So I'm going to graph my asymptotes in different colors in a second. And then again, we can graph this other coordinates. Our third coordinate at pi is 0. So from the pattern of it, all of the pi values are going to be located at 0. And guys, that should make sense, right? Because if you look at your unit circle, what is the slope of this one here that has y values of 0 when you divide 0 divided by 1 or whatever, right? This blue line has a slope of 0. On the other hand, the vertical line has an undefined slope, which is why at these coordinate points, we're going to end up having asymptotes. Okay, so our asymptotes, I'm going to draw in red. Just go ahead and those will be our vertical lines. So we're going to have one here at negative 3 pi over 2, and another one at negative pi over 2, another one at pi over 2, and another one at 3 pi over 2. Now, again, for the sake of time, I'm not going to go through your entire chart, but unlike your cosecant and secant graphs that look like parabolas that kind of flip out, tangent's a little bit different. If we were to look at the slopes of all the other points in the middle. So notice here we got a slope of 0. Here I'd have a positive slope. Here it's getting steeper. Here it's getting steeper. Here it's getting steeper. Here it is undefined. And then there it gets negative, and there it gets negative, and there it gets negative, but less steep and less steep, right? So if we were to actually take the time to look at that, perhaps my husband just sent me a very funny meme about asymptotes while I'm on this video, and you now know about it because he's hearing me teach you and apparently wants to partake. It's a very punny math meme about asymptotes, so go look at it. It has to do about phase shift and about mother functions. It's kind of funny. All right, anywho, difference here is instead of those parabola thingies that look like they flip out, based on slopes, this is what the slopes do in the unit circle. So this is what your tangent function looks like. And pardon my curves for being a little bit messy, but you get the idea. Okay, so this is what the tangent function looks like. All right, again, let's go ahead and talk about our details. So we've got period. Difference between this. Look at how long it takes for your cycle to repeat itself. That looks like one period. This looks like another. This looks like another. So that distance is from negative pi over 2 to pi over 2, which is just a distance of pi. Okay, our domain is the set of all real numbers, right? It covers every x except where our asymptotes are, which is going to be similar to the last graph we just did, pi over 2 in, but when n is an element of the odd integers. Is an element of the odd integers. My E looks a little bit weird, but you get the picture. Range, what y values does this cover? Well, heck, it covers all of them, all real numbers. It goes up and down forever. The x-intercepts, there are multiple of them. In fact, there are an infinite amount of x-intercepts that we cannot name them all, so I need to represent them. Notice this crosses the x-axis at all of the whole pi's. So I can say our x-intercepts occur at pi n, when n is an element of the integers. And the y-intercept, I'm sorry, I should have labeled that as an intercept. The y-intercept, it crosses the y-axis at 0. Okay, lastly, asymptotes. They coincide with our domain restrictions, as discussed before. So x is equal to, pi over 2n. Pi over 2n. When n is an element of the odd integers. So there is tangent. Okay, our last function that we need to discuss, as you may have guessed, is cotangent. Why? Well, because, recall, tangent of theta and cotangent of theta are reciprocals. Reciprocals. There we go. So in other words, if I have y, well, if I have 1 over the tangent of theta, that's the same thing as the cotangent of theta. So again, in your calculator, if you want to graph cotangent, you would have to put 1 divided by tangent of x in the y equals section. Now that you kind of get the idea of how things unfold, I'm not going to show you a table or anything like that for this one either. I'm just going to go through, we'll make our x increments. Again, we'll count by pi over 2. We got a positive 1, we got a negative 1. And again, if we were to take remember this is slope, but now it's 1 over the slope. Okay, so if we kind of keep that in mind, and I won't bore you with the super details of it, because I know I'm probably burning on your attention span here. Just trust me on this one. These have asymptotes at 0 and at pi and at 2 pi and at all of the whole pi's. So where the intercepts were for tangent, the asymptotes now are for cotangent. So again, there was a phase shift between the two of them. And since it's a reciprocal and things kind of flip-flop here, these graphs in between, they will intersect the half pi's, but they will also be flipped downward like this. So this is what the graph of cotangent looks like. The period of it matches the period of tangent. It only takes pi to complete one cycle. The domain is going to be all real numbers, except where our asymptotes are, which is going to be pi n, when n is an element of the integers, right? Because all of the asymptotes occur at those whole pi numbers. The range is going to be all real numbers, just as it has been. The x-intercepts occur at all of the half pi's, pi over 2, 3 pi over 2, etc. So we're going to represent that as x equals pi over 2n, when n is an element of the odd integers, just like before. The y-intercept does not exist, right? There's an asymptote along the y-axis, so our graph will never actually cross it. And speaking of asymptotes, our asymptote coincides with the domain restriction, which will be x equals pi n, when n is an element of the integers. So we've gone over all these details just to kind of always keep you on top of, thinking about domain and range and intercepts and asymptotes and things like that. Going forward for your test, you need to be more so familiar with, you have the aid of a calculator. So making sure that when you plug things in the calculator, you know that like if you want cotangent, you need to be plugging in 1 over the tangent of x in order to see your graph. And as long as you know how to manipulate your window, manipulate your table set, you'll be able to graph any of these other trig functions. And just know that your calculator will not show the asymptotes. You're just going to see blank space there, but you'll see the repetitive curves repeat themselves. So I hope this helps. Have a lovely day, fantastic weekend.